Hello. Today we are going to look at binary arithmetic, and that is for Unit 2. In this chapter, basically we are going to look at binary data arithmetic and logic operations. Basic arithmetic operations such as addition, subtraction, multiplication, and division is what we are going to be looking at in this chapter. There exist also logic operations where we use logic functions like the AND, the OR, and NOT, which are the basic logic functions. However, in this unit, we are going to limit ourselves to arithmetic operations only. Upon completion of this unit or this chapter, a learner should be able to do binary addition and subtraction on given two binary numbers. And it should also be able to do addition and subtraction on two given hexadecimal numbers, as well as be able to do or manipulate binary numbers using the 2's complement. Now let's understand some basic rules when it comes to binary addition. The basic principle of adding binary and subtracting binary are similar to what we would normally do when we are working with decimals. So for instance, in the instance where we would have a decimal, say 2 plus 2, whatever the principle is that we use in this addition where we would get 4, it is the same thing or the same principle that we would use in binary addition and subtraction. In this case, in the case of addition, adding 0 to a certain digit produces the same digit as the sum. And when we add 1 to a certain digit or another number in the decimal number system, the result is the next higher digit or number, as the case may be. Okay, so kindly take note of that. So for example, if we have 6 plus 1 in decimal, this would give us 7, because 7 immediately follows what? 6 in the decimal number system. Now, also, if we have 7 plus 1 in the octal, this will give us 10. As in octals, if you remember, in the octal number system, the next adjacent higher number after 7 is what? 10 or 10. Similarly, 9 plus 1 in the in the hexadecimal number system is what? A. That is, in the hexadecimal, we have 0 through 9, and then the next one is what? A. Now, having understood this background, we can write the basic rules for what? Binary addition. Okay? Now, let's look at these basic rules for binary addition. If we have to add zero if we have to add 0 plus 0 in binary, this will give us 0. If we do 0 plus 1 in binary, we would always get 1. If we do 1 plus 0, it's 1. When we do 1 plus 1 in binary, we would get a 0 with a carry of 1 to the next more significant bit. Okay, so if we have 1 plus 1 plus 1, it means that we would end up having 1 because we already have 1 plus 1, which gives us what? A 0. And then a 0 and a 1 would give us what? 1. And in this case, we would have a carry of 1 to the next most or more significant bit. So kindly take note of that. So from this table here, you would find binary addition of 3 bits. Okay, that is, we have A, B, and then carry in. So 0 plus 0 plus 0 would give us 0 as the sum. And then we would get a carry out of 0. 0 plus 0 plus 1 would give us 1 with a carry out of what? 0. 0 plus 1 plus 0 would also give us a sum of 1 with a carry of 0. However, 0 plus 1 plus 1 would give us 0 with a carry of 1 when you look at rule 4. Okay, it goes on like that because we are looking at 3 bits, so you would have the combinations for what? 3 bits. Okay, all right, so let's move on. Having understood this basic principle, we can then move on to look at the basic rules of binary subtraction. Now, for the basic principles of binary subtraction, if we have a 0 minus a 0, that will automatically give us a 0. Okay, so that would give us a 0. Now, if we have a 1 minus a 0, it will give us a 1. If we have 1 minus 1, that will give us a 0. And if we have 0 minus 1, that will give us what? 1. What this basically means is that for binary subtraction, if you have 2 binary digits, you would always get a 0 when the binary digits are identical. But where you have at least one of those binary digits being not the same, you would get an output of 1. But in the case of 0 minus 1, you would get the output as 1 with a borrow of 1 from the next more significant bit. So kindly take note of that. Now, addition of larger bit binary numbers. The addition of larger binary integers or fractions or mixed binary numbers is performed column-wise, just as we would do in the case of decimals. Okay. Now, in the case of binary numbers, however, we follow the basic rules of addition of 2 or 3 binary digits as outlined earlier, or as we looked at earlier. The process of adding two larger bit binary numbers can best be illustrated with an example, which we are going to look at pretty soon. Okay, so let's consider that we have two 4-bit binary numbers where we have A1 is the proper representation. So we have A0, so we have A0, A1, A2, A3. Then we have B0, B1, B2, and B3. Okay. What we do here is that we add the LSBs or the LSB bits and record the sum below the bits. So whatever we do here, assuming we're going to represent our output with C, after adding so this, we would have what? C0, C1, C2, C3. Okay. We can also get some carry when we do the addition. So assuming we do addition of A0 and B0, and we write the sum here, and there is a carry out, okay? The carry out would now be brought to the next column, and then the addition would continue. So we have, in example 1, we have A0, and then B0. This gives us sum 0. If there is a carry, we bring the carry to this column and then we continue. When we move on, we do the next one. We get S1, and if there is a carry, the carry move on to the next column. Then we would get what? S2. If there is a carry, that will be carry 2. That will be moved to the next column until we get the final what? S3, and then what? A carry. All right. Now let's look at addition using the 2's complement method. Now the 2's complement is the most commonly used code for processing positive and negative binary numbers. It also forms the basis of arithmetic circuits in modern computers. When the decimal numbers to be added are expressed in 2's complement form, the addition of these numbers, following the basic laws of binary addition, would give us correct results. The final carry obtained, if any, while adding the most significant bits, that is, in this case, if it were in the case of A3 and B3, if we get the final output and there is a carry, say C3, we disregard that carry. This is normally thrown away. we don't use it. Okay? So to illustrate this, we will consider the following 4 different cases. That is, we will consider the first case where both numbers are positive. We would also consider the case where both numbers, or the larger of the two numbers, is what? Positive. The larger of the two numbers is negative. And also what? The two numbers are negative. So let's quickly look at these examples. Now, consider the decimal numbers 37, or positive 37, and positive 18. The 2's complement representation of 37 is 8, or in 8-bit representation, is 0, 0, 1, 0, 0, 1, 0, 1. Here, this binary digit here basically means we have 1, 2, 4, 8, 16, 32, 64, and 128. That is 8-bit. Now, if we take it that way, then it means wherever you see a 1, here we have 32 plus 4, which is 34, plus 1. Okay. Now, for 18, we have of positive 37 in 8-bit, you have 32 plus 4, which is 36, plus what? Plus 1, which will give you 37. Okay. Now, for the 2's complement of 18 in 8-bit representation, we would have 0, 0, 0, 1, 0, 0, 1, 0. So if this is 1, 2, 4, 8, 16, 16 plus 2 would give us what? 18. So that will be the binary representation of these decimal numbers. Now, the addition of the two numbers, that is 37 and 18, is performed as follows. So, we have 1 plus 0, which is 1. 0 plus 1 is 1. 1 plus 0 is 1. 0 plus 0 is 0. 0 plus 1 is 1. 1 plus 0 is 0. 0 plus 0 is 0. 0 plus 0 is 0. So the decimal equivalent of this now becomes 0, 0, 1, 1, 0, 1, 1, 1 in binary, which is the positive, or the equivalent of what? 55, which is the correct answer. Okay. Now, let's consider case 2, where we look at a positive number and a negative number. Okay. Now, The 2's complement for 37, which we already looked at, is 0, 0, 1, 0, 0, 1, 0, 1. Now, the 2's complement representation of negative 18 in 8-bit representation is 1, 1, 0, sorry, 1, 1, 1, 0, 1, 1, 1, 0. Now, if we want to do the addition of these two numbers, the final answer we would get here will be 1 plus 1 would give us, 1 plus 0 will give us 1. 0 plus 1 will give us 1. 1 plus 1 will give us 0 with a carry of 1. When that carry comes here, plus 1 will still give us 0 with a carry of 1, which comes here. So 1 plus 0 will give us 1. 1 plus 1 would give us 0 with a carry of 1, which comes here. This plus this gives us what? A 0 with a carry of 1. And then we would get 1 here, plus 1, which will also give us 0 with a carry of what? 1. But if you remember the rules, we are supposed to discard this. If we add this, it is going to give us a wrong value. Okay? It is going to give us a wrong value. Okay? All right. So, if we do this, we would get what? 19, which is the correct answer. Okay? Now, let's consider two decimal numbers. That is positive 18 and negative 37. So negative 37 in 2's complement form in 8-bit representation gives us 1, 1, 0, 1, 1, 0, 1, 1. Positive 18 gives us 0, 0, 0, 1, 0, 0, 1, 0. Now, if we do this addition here, the answer we are going to get would be what? Negative 19. Okay? Which is in the 2's complement form, we would get negative 19, which is the correct answer. If you were to even do decimals, where you have negative 37 plus positive 18, the answer you would get is what? Minus 19. So that is it for case 3. Now let's look at case 4, where you have all of them being negatives. Now, in the negative sense, the 2's complement of 18, which we already knew to be 1, 1, 1, 0, 1, 1, 1, 0, and then negative 37 in 2's complement, which we know to be 1, 1, 0, 1, 1, 0, 1, 1. If we do this addition here, the answer we are going to get if it were to be in decimal will be negative 55. Now, let's do this binary addition and see what we end up getting. So in this case, we have 1 plus 0 from our rules is 1. 1 plus 1 is 0 with a carry of 1, which when added to another one will give us 0 with another carry of 1. 1 plus 1 plus 1 is 1 with a carry of what? 1. When added to this would give us what? 0 with a carry of 1. When added to this would give us 0 again with a carry of 1 here. And this will give us 1 with a carry of 1. When added will give us what? 1 with a carry of what? 1. But we discard this one. If we were to maintain the 1, then in our final binary equivalent of these large numbers, okay? Now, for subtraction of larger bits binary numbers, subtraction is also done column-wise, the same way as in the case of decimal number systems. Wherever the subtrahend, that is the bit to be subtracted, is larger than the numeand, which is we borrow from the next adjacent higher bit position, having 1 as an example. Let us go through the different steps for subtracting 1 0 0 1 from 1 1 0 0. So in this case, 0 minus 1, if you remember, would give us what? 1. Zero minus 0 would give us, because we are borrowing, we would get what? 1. Okay. Then the next step, we would get 0 minus 0, which will give us 0. And then we have 1 minus 1, which will give us what? 0. So that is the representation of larger bits subtraction of binary numbers. Now let's look at subtraction using 2's complement arithmetic. Now in this case, adding 2's complement of the subtrahend to the minuend and disregarding the carry, if any, achieves subtraction. The process is illustrated considering 6 different cases. So we will look at when both minuend and subtrahend are positive. The subtrahend is the smaller of the two. We would also look at when both minuend and subtrahend are positive. The subtrahend is the larger of the two. The minuend is positive. The subtrahend is negative and smaller in magnitude. The minuend is positive. The subtrahend is negative and greater in magnitude. Both minuend and subtrahend are negative. The minuend is smaller of the two. And both minuend and subtrahend are negative. The minuend is larger than the two. Okay. Now let's look at case 1. Alright, so let's look at case 1, where we have to subtract 14 from 24. Now the 2's complement representation in 8-bit for 24 is 0 0 0 1 1 0 0 0. The 2's complement for 14 is 0 0 0 0 1 1 1 0. Okay. Now, when this is added, what it basically means is that, when we do subtraction here, what we are going to be doing here basically is to have positive 12 minus positive 14. Okay, and then the answer here would be positive 10 if it were to be in decimals, but in binary we would get 0 0 0 0 1 0 1 0. Okay, that is, if we do from the LSB, 0 minus 0 would give us 0. 0 minus 1 will give us 1. 0 minus 0 will give us 0. 1 minus 0 will give us what? 1. 1 minus 1 would give us 0 with a carry of 1, which when done similarly for the subsequent 3 bits, we would get 0 0 with a carry of 1, which we would discard. Okay, so that is case 1. Then in case 2, we have positive 24 being subtracted from positive 14. Now, in that case, it will mean that when we have the 2's complement of 14 and then the 2's complement of 24, because 24 is now the subtrahend, the 2's complement of the subtrahend does become 1 1 0 1 0 0 0. Okay, and then with that we can now find the arithmetic of same, and that will give us negative 10. Okay, all right. Similarly, when we do that we subtract 14 from 24, then it means that the 2's complement of 24, which we already know, would now be the minuend. Okay, and then the 2's complement of negative 14 will be 1 1 1 0 0 1 0, and that becomes the subtrahend. When we find the 2's complement of the subtrahend again, that will give us 0 0 0 0 1 1 1 0, and therefore positive 24 minus 14 is performed as shown below, and that will give us positive 38. Okay, so you take note of that. Then in case 4, we are subtracting 14 or negative 14 from 24. So you have 24 minus 14. And in this case, we would have our 24 being the minuend, and then we would have our minus 14 being the subtrahend. So we first find the 2's complement of the minus 14, which will give us 0, 0, 0, 1, 1, 1. Sorry, 0, 0, 0, 0, 1, 1, 1, 0. Therefore, we would get plus 24 minus 14, which will end up giving us positive what? 38. Okay, so you take note of that. Then case 5, where you have all of them being negative. That is, you're subtracting 14 from minus 14 from minus 24. So minus 24 now becomes the minuend, and then minus 14 becomes the subtrahend. So you find the 2's complement of the subtrahend, and then you perform, and you would get minus 10 as the answer. And then similarly for case 6, you have minus 24 from 14. So in this case, minus 14 becomes the minuend. And then minus 24 being the subtrahend, we find the 2's complement of the subtrahend again, and then we perform that operation, and that will give us positive 10. Now let's look at this example here. Subtract 1110.011 to the base 2 from 11011.11 using the basic rules of binary subtraction, and verify the results by showing equivalent decimal solution. Now, the minuend and subtrahend are first modified to have the same number of bits in the integer and fractional parts. Okay, so if you look at the integer parts, we have 1, 1, 1, 0. And then at the fractional part, we have 0, 1, 1. So we have 4 bits for the first one, and then its decimal part has 3 bits. And then for the second one, so here we have 4 bits, here we have 5 bits. And then here we have 3 bits, and here we have 2 bits. So what we have to do is that we would have to do modification to ensure that all the bits are the same. So if you take the minuend, which is 110011.11, the integer part has 5 bits, which is this. So we would have to convert its fractional part to 3 bits to be similar to the subtrahend. So we would have 1, 1, 0. And then for the subtrahend, which is 1, 1, 1, 0, we would add 0 to the most significant bit to give it 0, 1, 1, 1, 0. And then we would have 0, 1, 1 as the fractional part. Okay. Now, the decimal equivalents for these binary are 27.75 and 14.375 respectively. Okay. Now, if we are to find the difference would give us 13.375, which is the decimal equivalent of 0.1101.011. Now, what I want you to do is to try your hands on these examples. Subtract A, which is minus 64 to the base 10 from positive 32 to the base 10. And then B, 29.A to the base 16 from 4F.B to the base 16 using 2's complement arithmetic. Similarly, perform the following operations using 2's complement arithmetic. The numbers are represented using 2's or 10's or 16's complement notation. As the case may be, express the results both in 2's complement binary as well as decimals. And then for number 3, perform the following operations using the 2's complement arithmetic. So take these try questions as an assignment, which you don't have to submit, but you have to just try your hands on them. And also try your hands on question number 4 as well. Now, let's look at binary multiplication. The basic rules for binary multiplication are governed by the way an AND gate functions when 2 bits are to be multiplied, are fed as the inputs of the gate. So for a basic AND gate, you would have 2 inputs, A and B, and then you have the output, let's say Y. It would be easy to say that the result of multiplying 2 bits is the same as the output of the AND gate, with 2 bits applied as the input. So the basic rule here would be that if we have 0, 0, or if we have A as 0, so let's say this is A and this is B. If we have 0, 0, we would get 0. If we have 0, 1, we would get 0. If we have 1, 0, we would get 0. And then if we have 1, 1, we would get what? 1. So that is the binary, or the basic rule for binary multiplication. Now, let's look at the signed magnitude system. Now, in this system, the leftmost bit of a binary number is the signed bit. So the signed bit is 0 for positive and 1 for negative binary numbers. So the magnitude bits are in true or uncompleted binary for both given positive and negative numbers. So for example, if we take the decimal number 13, which is expressed in binary as 1101, which is 13, in a signed magnitude system, then we would get 01101. So this becomes the signed bit, and this becomes the magnitude bits. Similarly, if we look at a negative number, the signed bit would be what? Positive. Sorry, the signed bit would be 1, and we would get the magnitude bits to be the same as 1101. Okay, so take note of that. So notice the only difference between positive 13 and negative 13 is the signed bits, because of the magnitude. Bits are in what? True binary for both positive and negative numbers, as we looked at earlier. Now let's look at this example. Express the decimal minus 25 as a binary number using sign magnitude system. Now, if we take 25, its real binary bits, okay, or magnitude bits will be 1, 1, 0, 0, 1. Okay. Now, because it is negative, its sign magnitude, or sign bit, sorry, would be what? 1. And so we would end up getting 1, 1, 1, 0, 0, 1. So here, what it means basically is that you have 1, 2, 4, 8, 16. So 16 plus 8 will give you 24, plus 1 is what? 25. And that gives us the real magnitude bits for 25. And because it has a signed magnitude, the signed magnitude now becomes what? 1.